Okay, very well. Let's start our lecture number 19. And today we are going to establish the final form of Maxwell's equations for time-varying fields. And the outline of our lecture, we are going to talk about the second important element that connects electric and magnetic quantities, which is the displacement current. It was introduced by Maxwell to fix Ampere's law due to violation of the principle of charge conservation, as we will see in detail in this lecture. And then we are going to write down Maxwell's equations. We are going to revisit the terminology that we employ to name quantities, electromagnetic quantities, mostly in electrical engineering. Names are slightly different. In physics, magnetic field and magnetic flux density are interchanged. In physics, in magnetism, one of the areas of physics. In EE, we have a distinction. We call it different names. Okay. So we're going to talk about displacement current. We're going to put down the Maxwell's equations and finally derive Poynting's theorem and make an interesting example of using this theorem. The references for this lecture are Jackson's chapter 6, Jackson's book, and our ebook on chapter 6 as well. Let's revisit the principle of charge conservation. Let's talk about this theme here, displacement current. Suppose we have a closed surface. Let's call it sigma. Let me put down here. The closed surface is sigma. It encloses a volume V. We might have some charge inside of this volume. The charge might be crossing the boundary outwards or inwards. You might have a charge accumulation, or you might have charge flowing away from the volume. So let's call the volume, the surface differential element, the sigma vector. Volume is V, charge is Q, and the total current that flows through the surface we are going to call I. So principle of charge conservation establishes that the positive flux of charge through the surface, a positive current, let's say, must balance the rate of change of charge inside of the volume. So if charge is decreasing, we have a minus sign in front, so we have a positive result. So it means that I is flowing out of the volume. So you have the minus. On the other hand, if I is a negative quantity, in other words, the flux is negative, is inwards, it means that charge is accumulating in the volume. So dq dt is larger than 0, but then you have a minus sign to make it right. So if we write that in terms of the field quantities, current density to calculate current flux, and charge density to calculate charge, you're going to have this equation. The flux of J through the surface outwards equals to minus the total derivative of the charge, which is the integral of rho dV. If we use Gauss's theorem, something that we have done already a number of times, if we use Gauss's theorem, to transform this into a volume integral. Then we use a differential volume to demonstrate that we have this continuity equation. That's something we spoke about on chapter 4, when we spoke about conduction, right? Electrical conduction. So what are the implications of the principle of charge conservation on one of the Maxwell's equations for the magnetic field, which is Ampere's law in differential form? right? So what are the implications? What happened? Originally, we have this equation here, and this we said we have this in the regime of if you calculate, right, for time varying fields, the divergence of both members of this equation, we know that divergence of the curl is always 0 independent of h. So it means that if I apply the divergence on each side of this equation, right, I'm going to have 0 equals to divergence of j. And this violates the principle of charge conservation. I just showed to you that principle of charge conservation establishes that divergence of j equals to minus d rho dt. In other words, for time varying fields, j is not solenoidal. And on the other hand, Ampere's law in differential form implies that j is solenoidal. So something is wrong. We have to fix this relationship here. What Maxwell did was to include what he called a displacement current density on the right-hand side of Ampere's law. Okay? So, in such a way that the divergence of the right-hand side in Ampere's law would be 0. In other words, he added this displacement current density on the right-hand side, so that now, if I apply the divergence, I'm not going to violate, for a given specification of JD, I do not violate the principle of charge conservation. We are going to call it PCC, okay? So let's apply now how to fix the problem. Let's apply the divergence on both sides, which is an identity equals to 0. It means that divergence of j plus divergence of jd equals 0, or this displacement current density has has to be chosen such that the divergence is minus the divergence of j. Okay? So if we use the continuity equation, recall that divergence of j equals to minus d rho dt. So it means that divergence of gd equals to plus d rho dt. So what is jd in this case, right? So so in other words, if we replace rho, we have this equation here, right? So divergence of jd has to be chosen as plus d rho dt, right? So, but on the other hand, there's one equation, one Maxwell's equation, that establishes that divergence of d. I have to be careful not to make this tilted Greek letter, like an italic Greek letter, make it different from the traditional Greek letter, non-italic Greek letter. So it means that the rho is time varying. So if we use this equation and plug that in here, this is going to be d rho, I can write like this, ddt of divergence of d, or divergence of dd dt as well. This is a round letter. And I can combine these two relations, right? So I have divergence of jd minus dd dt equals 0. So what can we do here? I mean, jd is going to be equals to this. It's one possibility, but the general solution of this equation is jd equals to dd dt plus a vector that has 0 divergence, plus a solenoidal vector, and any solenoidal vector can be written as the curl of another vector. This is, I'm going to call this cursive v, okay? It's a vector v, a cursive v. So that's the general solution for JD. So JD has this form, whatever choice I have for this, for this rounded V, okay? So we're just going to choose V such that the curl equals to 0. Right? So let's choose a solenoidal V. So in this case, JD is equal simply to dD dt. Right? So we can do that. So if we do this choice, this fixes Maxwell's, Ampere's law in differential form. So, the question is this, does it work? Well, a way to demonstrate this is to write Maxwell's equations in this form and try it, and then see if it explains all the experimental evidence of the existence of electromagnetic propagation and a relationship between fields and the functioning of devices. So, in fact, this has been demonstrated by several experiments afterwards, after Maxwell's formulation, right? So, in summary, now Maxwell's equations for H is curl of H equals to J plus JD, with JD given by this relationship here, or if you write in terms of fields, curl of H equals to J plus the displacement current density, which is given by the time variation, time rate of change of the electric flux density vector relative to time rate variation, right? So also the introduction of this term here, of this displacement current density, it fixes the capacitor paradox, a well-known paradox, in which if we look at the capacitor and a time-varying current in a circuit, right? So we know that the current flows through the capacitor. In the DC regime, for a constant I, we know that the current doesn't flow, right? You just charge the electrode, the positive electrode, and no further current until the transient is finished. After the transient, you have a zero current. But for time-varying current, we know that the current flows in a circuit that has a capacitor, right? So, but look, if we look at if we use the integral form, let's look at the integral form of this one. Means that the circulation of H is the total current that is enclosed, right? If I make a closed path, if I use different surfaces, right, bound by curve C, I have different surface here. Okay, that's one surface. There's another one that's, they have in common, they have the same bounding curve. The border of the surface is C. So I can calculate the circulation of H through C. Let me change the color here. So this is one surface, the red one is the one that's inside, right? So that's the red one, red surface here. There's the other one is the black one that's outside, right? So you have two surfaces. One is sigma 1, and the other one is the black one, is sigma 2. So it means that the circulation of H around the path C equals to either the total current through sigma 1 of J plus JD, right? The sigma must be the same through sigma 2. So it means that it equals to the I'm going to call it like this: I plus I displacement through sigma 1, which must be equals to I plus displacement current through sigma 2. Must be the same result, right? So if you look at this situation here, I have drawn, this is one piece of the wire of the circuit, right? We're looking at this thing here. We have make a loop, a zoom. We have zoomed that region. This is the wire, okay? Obviously, on the wire, that's a conductor, the D equals to 0, okay? So there is no JD, no displacement current in the wire, let's say. So if I calculate Ampere's law through path C, it must correspond to the current that flows through either the green surface or the current that flows through the blue surface. In the green surface, D equals 0, and the current that flows is equals to the free currents through the circuit, right? On the other hand, if I use this surface, the current that flows, I have a D that's different than 0, I have a field here, right, between electrodes, E field, and also have a D field as well. So there's no free currents because there's no conductor here, there's only displacement currents. So you're going to have the situation in which you have JD different than 0 between electrodes and J equals 0. And here in the conductor, you're going to have JD equals 0 because D equals 0 and J different than 0. So that solves the capacitor paradox. If I didn't have displacement current, if I calculate Ampere's law through this surface green, it would be the free current, I. If I calculate here, it would be 0 because there's no displacement current, right? So the displacement current solves the capacitor paradox. So that's what we have, right? So this is what we have. I mean, through sigma 1 is the free current, through sigma 2 is the displacement current, which is equals to the same. It is equals to the free current as well. They are the same because of charge conservation, right? So that's the final connection we needed to conclude our Maxwell's equations. Now we have a set of 4 equations. Let's review them. We have in differential form, we have curl of E equals to minus the time rate of change of B, right? Faraday's law, which originates the differential equation. This is the specification of divergence of the electric flux density vector, which is the free charge density. Curl of H now is J plus displacement current density, which is dD dt, and the specification that B is a solenoidal field. This is a set of 4 equations. As I mentioned earlier in this course, we can write down those equations in a T-shirt. Have a nice, beautiful T-shirt, right? 4 Maxwell's equations, and we have integration using the Stokes theorem and the Gauss's theorem. Then we can show easily that the circulation of E equals the total rate of change with minus sign in front of the magnetic flux, right? The total flux that goes outwards a volume is equals to the bound by sigma is equals to the total free charge, right, in the volume that is bound by sigma. That's just showing you the domains here, right? That's the geometric construction we must have. Sigma is the surface that bounds, that encloses V, and the sigma is always outwards. And for the line integral, C is a path that encloses the area. It doesn't have to be a plane area, it might be a curved area. It's the border of that curved area if you want, or just a path that encloses the area. And always you move around the path using right hand rule. Okay, so we are calculating things. I mean the sigma must go to the to the thumb direction, right? So so we have circulation of age equals to the total current, which is the free current plus displacement current, which is the total derivative of the electric flux. And finally, the magnetic charge enclosed by a surface is always equals to 0. Okay. Also, we need constitutive relations. In general, D, E, and P. P is the polarization vector. If you have a set of dipoles in one material, you can define a polarization. You can have this general constitutive relation. Also for B, the same. This has a typo here. It's mu0 times H plus M. Here is epsilon 0 E alone plus P without epsilon 0. Here is mu0 times the sum between H and M, which is the magnetization. In conductive media, we have a relationship between J and M and E for linear, isotropic, and conductive media. That would be a relation, right? We are going to show that we can use, we might not use the conductivity. We can use a permittivity that relates everything. We can define current, relationship between current and the field and so forth. We'll see that we can generalize, we can introduce the conductivity in the permittivity function of a material. We can do that, okay? And also, I mean, we might encounter, let's say, more complex materials, not only made by magnetic dipoles or magnetic or electric dipoles, but then the general relationship that we must write is like this. D is a function or some type of function, depends on the material, of E, okay? It's a vector function of E, right? B as well is a vector function of M, or in more general way, we can have more generally, we can talk in more general ways, E and H, right? H might influence D somehow in this material, this generic material, and B is also a constituted more general relation that is B might be influenced by either E or H as well, right? In general, these are only functions of one of those. For instance, D is only a function of E and B is only a function of H. But in certain types of materials, we might have an influence of the E field on B and the influence of the H field on D. So we might get more complex, relations between those things. So, but I mean, in general, 99.999% of the case, we use the standard constituted relations, which are those here, okay? Let's review quickly the terminology and SI units of those fields. E is called the electric field, the standard. That's the field that was defined to allow determining the force on a point charge, on a test charge, right? So the E field is that quantity. So the auxiliary field is the electric flux density vector measured in coulombs per square meter. This is also called, in the area of physics, is also frequently called electric displacement vector as well, right? B is called the magnetic flux density. It has the same properties as D in terms of flux. We have electric flux, magnetic flux. So these quantities are flux density quantities. B is called the magnetic flux density, and also called in the area of physics, it's called the magnetic induction vector, measured in Tesla. right? Weber per square meters. H is called the magnetic field, measured in amps per meter, amperes per meter. P is the polarization vector, measured same unit as D, coulomb per square meters, polarization vector, which is the density of dipoles in a material. M is the magnetization vector, measured in amperes per meter, which is the density of magnetic dipoles in a material. Rho is the free charge density. Don't forget this word here, free, right? It's not, no bound charge enters in the definition of rho. This is a free charge. These are charges that move across the circuits between electrodes in an ionic gas, for instance. These are the free charges, right? And also J, again, is the free current density. We're talking about free carriers moving in a circuit. That's the type of current we're talking about. So the free charge density is coulomb per cubic meters, and the free current density is amps per square meters density, right? It's a flux type vector. That's why it's per unit area here. And finally, we have vacuum permittivity, which is a number given by 8.854 times 10 to the minus 12 farads per meter. Equivalent, that's an approximately equals to 10 to the minus 9 divided by 36 pi. Right? That's a nice way to remember the value. 10 to the minus 9, 36 pi. And mu 0 is the vacuum permeability, which is 4 pi times 10 to the minus 7 Henry per meters. So let's recall, farad is the unit of capacitance, and Henry is the unit of inductance, right? Also, we need when we have to solve Maxwell's equations, we might have different media involved, and we have to employ boundary conditions because we are solving differential equations in those problems. So we have equations which we call the divergent equations. So Maxwell's equation has 4 equations. 2 of them specify divergence. The other 2 specify the curl. So divergent equations are written in this form, right? I mean, in integral form, the divergent equations yield the flux of a vector through a surface equals to the quantity which is enclosed, which is either electric charge or magnetic charge, which in that case is going to be 0 value. But G is always a density function, either magnetic charge density or electric charge density, but magnetic charge density is 0. So, but the general relation for the divergent equations are those flux relationships. These are the Gauss's law type equations, okay? And the other one is the Kerr equations. We have I mean, in the volume, if we integrate both sides of the Kerr equation, have a volume. This is wrong. This is wrong. Let me just. This notation is wrong here. Okay. The volume integral. If you apply the volume integral of the curl, it's going to be the volume integral of the whatever is on the right hand side. So this is a volume integral here. Volume, right? Do that. Then we use that vector theorem, which allows us to express this integral. This is the dual relation, like Gauss's theorem, right? But it's related to the curl. So we have that integral transformation that we go from the volume integral to the surface integral of the cross product between the sigma and the vector field. So the Kerr equations, in essence, yield this type of relationship. We have, you know, surface integral in a closed surface of the cross product between the sigma and f equals to the volume integral of the density or of the quantity that's on the right hand side, which you call capital G vector. Okay, so if we apply these relations for a boundary between two media, we're talking about those generic relations. We have a medium 1, a medium 2. N is the normal that goes from 1 to 2. H is the height of this Gaussian-like, Gaussian type of surface. We make integrals on volumes and on surfaces. So the divergent equations yield in the limit, the flux in the limit that H goes to 0. We are talking about fields, right? These are fields, either E or H. I mean, either D or H, or B, right? So we have either D or B. On the right-hand side, we have a density. So that's going to be, if we have a surface charge, surface density, this gives delta sigma. As H goes to 0, that's going to be delta sigma times the surface, this rounded G, surface density function Js. Okay? And on the other hand, when we make the limit of H going to 0, we are going to have a contribution on the top surface. It's going to be here, it's going to be F side 2 delta sigma N minus F side 1 delta sigma N plus something proportional to H plus a vector alpha proportional, and I mean the flux through the lateral surface is going to be proportional to H. That's the flux. But we are talking about fields, okay? And fields cannot be confined to a surface. They occupy a volume. So when H goes to 0, we don't have a field surface. Okay, we don't have that. Fields are immaterial quantities. They do not depend on material. They are just fields. So they occupy volume. They spread across the volume. They cannot be confined to a surface. So this goes to 0, and the result is going to be something times delta sigma here. The relation that we have, lateral contribution equals 0, and the surface density, we have delta sigma. Then we, these are common factors, we eliminate them, so we have the boundary condition. So this is called the surface density, G. Okay, we are going to identify in the proper Maxwell's equations. So that's the result we obtain for boundary conditions that are resulting from the divergence equations that gives the flux and gives this boundary condition. I mean the n dot, the difference between vectors on both sides of the interface, equals to the surface density function, which we are going to identify in a moment. The curve equations, on the other hand, we make the same principle, right? The limit as H goes to 0 of this integral equals to limit of this volume. Again, this in a limit, this might be a current density, for instance. This might have a limit, okay? A surface current. So this is going to be delta sigma times J of on the surface. On the other hand, this integral is going to have contributions on the top hat, on the top surface of the cylinder, the lower surface, which are going to be proportional to delta sigma here, right, times that. So delta sigma and delta sigma cross product with F on side 2, and delta sigma cross product of F on side 1. On the right hand side, we would have delta sigma times GS, so we cancel those terms here. And we have a lateral contribution, which is proportional to H again, another vector, I mean, this integral has a lateral contribution proportional to h. Again, this we are talking about fields. Those are fields. Fields cannot be confined on an interface. So this goes to 0 as h goes to 0, and we obtain this equation. So in summary, the boundary conditions we get are those. There's a discontinuity in the normal component of fields equals to the surface density, right? Whatever that density is. The other one is that there's a discontinuity in the tangential components of fields, which is this equation here. Right? These are the general relations equals to J surface. If we have a density vector of material of a material thing, for material current, current density on the surface, that's going to be here, right? So let's identify now in our Maxwell's equations the divergent. Well, one of the equations is for D, right? So one equation N. This one, we have one is divergent of D equals to rho. So in this example, this is G, and this is F. So what do we get? Let's move to the next page. We have N dot D2 minus D1 equals to rho, tilted rho, on the surface. So there's a discontinuity in normal D, the normal projection of the displacement vector, electric displacement vector, equals to the surface charge density. The other equation is N dot B2 minus B1 equals to the surface charge density, but I mean the magnetic charge density on the surface, which equals to 0. So we have this boundary condition involving B normal, right? So there's a discontinuity in normal D equals to rho S, continuity of normal B in a boundary between two arbitrary media. The other equation is N cross E2 minus E1. This comes from Faraday's law, right? Well, this equals to minus dB dt surface B, right? We don't have that. We don't have a surface in the limit. This is going to be 0. There's no magnetic flux density on a surface. A surface magnetic flux density doesn't exist. It's always B also occupies a volume. So this is equals to 0. So we have this equation here. I'm going to erase. So when we have field, we don't have confinement. We can only confine charge on a surface and current on a surface, but no fields. Fields cannot be confined. So you don't have surface density of fields. So cut that, equals to 0. The other equation is N cross H2 minus H1 equals to, well, the free current density Js on the surface plus the displacement current surface charge surface density of displacement current. But this is Jd equals to dd dt. And there's no way you can confine a vector D on an interface. So this term equals to 0. You don't have, because this is not a material quantity. This is a field quantity. It's the time rate of change of the electric flux density. But this is a material quantity. You can have a current density on the surface, a surface current density. You know, you can have that idealization. We can have that. So that's going to be the boundary condition for, for H. So these are the 4 boundary conditions that we get, there's a discontinuity in normal D, which is the surface charge density. There's a continuity of the normal component B equals 0. The tangential E field is always continuous across the interface. And there's a discontinuity of H, which is given by the surface current density. Okay? Let's make some important remarks. As I mentioned to you, on the existence of surface densities. Okay, as I mentioned, there's no localized surface fields. You don't have localized surface fields. The fields can occupy a very narrow region across the surface, but they cannot have a zero dimension. Fields must spread on a volume, so they distribute in volumes. The other boundary condition, we call this the surface current density. Special letter K, this rounded, just this cursive type, just to mention that this is a time varying quantity. So this is an idealization for a perfect conductor. We might have a surface current density for a perfect conductor. If you have a real conductor, J distributes in the volume conductor. So we don't have that. That would be 0, in fact. And for dynamic fields, the K is always equals to 0, unless we have some special cases. We might have some different conductors. We might have some surface current density generated. But in general, dynamic fields, the current occupies, I mean, the current follows the field. The current is, in a perfect conductor, current is equals to a factor times the E field, and the E field spreads on the volume, so the current must spread on the volume as well. Okay. On the surface charge densities, well, we might have those if we have a contact between an insulator and a conductor, and also between conductors. We might have a charge accumulation on conductor. That's the fact, right? In the static regime, the rho s, the surface charge density, is specified independently in several problems. But for dynamic fields, rho s is determined after you obtain the fields. It's not an independent quantity. It depends on the fields on each side of the interface. So rho s is determined after you solve the problem. It's not something that you specify independently. But that is the case when you have a static regime. Okay? So these are the remarks that we want to make related to those those quantities. Well, there's an important relationship that specifies the energy in an electromagnetic system, and the connection of time rate of change of energy and power flow in an electromagnetic system, which is called the Poynting's theorem. Let's define this vector, this S cursive here, the rounded S, equals to the cross product between E and H. Why is that, right? Well, it gives a direction, which is the direction of the cross product, and the dimension of S. If we look at S, the dimension E cross H is is volts per meter times amps per meter, equals to volts ampere per meter square. Volt times ampere equals to watts, right? We know that from circuit theory. You can calculate if you want, right? That's going to be watts per square meter. So it's a kind of power density quantity, right? Power per unit area. So that's what it's going to be. Let's play around with this cross product. And as we want to calculate the flux, if we envision S as having a as being a flux density vector, we want to integrate the flux density vector, you know, on the surface. We want to do this, right? We want to make a closed surface. We can, for instance, if this is the sigma and we have S, we want to calculate what is the flux that goes outside or inside, right? And this by Gauss's theorem is equal to the volume integral of divergence of S. Okay? So let's then calculate what is the divergence of this vector. Is the divergence of the cross product. We have a vector identity that can that expands the divergence of E cross H. It's like this: H dot curl of E minus E dot curl of H. Then we use Maxwell's equations. This one here is minus dB dt. This one here is J plus dd dt. Then we have, you know, H dot dB dt. Then we have E dot J and E dot dd dt. So we're going to have something like this. Then we calculate, you know, the integral of divergence like this. We are going to calculate this inside. So it's going to be minus. So what's the flux of J to a closed volume? Inwards. Right? It's going to give us physical meaning quantity. So what's the flux? So is the volume, I mean, I'm calculating minus the volume integral. Okay? So it's going to be plus H dB dt, which is here. Because I have a minus with a minus H dB dt. Okay? Here we have minus JE with minus equals to plus, is right there. The other term is E dot dd dt minus, which is plus, right there. So that's what we have. So we know what those things are already, right? We saw this before. This integral before. This is a power exchange between free carriers and the E field. So it's a power exchange between these quantities. So this is power, right? So this is a type of power flux inward, is used partly to move the carriers, you know, back and forth, right? Or else, if the carriers give energy to the field, this might be a negative quantity, you know. So there's flux going out of the surface. And this one here has a dimension, the right dimension, is the time rate of change of energy. We call the electromagnetic energy. So this whole integral here is the time rate of change of the EM energy. W, you know, cursive type of W, electromagnetic energy. This term is this integral here. Let's take a look on these things here, right? I'm going to take a look there. So WEM has a rate of change. Let me just see the type of letter I'm using. Yeah. EM, this capital EM, okay, equals to volume integral of E dd dt plus B H dB dt. Sorry, H dB dt. Right? We have that the energy, a little exaggerate here, electromagnetic energy is the integral in time, right? So this is going to be an integral of a density function we are going to write here. This is just the same letter, but smaller, is a lowercase w. This is an uppercase. And what would be WEM? Well, WEM is simply the time integral. Okay, I can integrate this expression here. Integrate. I can at time t, for instance, what's the energy, right? I can say that W at time t. Let's assume that at time t equals 0, there is no energy, right? So until time t, this is going to be equals to integral from 0 to t of the integral, volume integral. Then we have a dt prime here, okay? Then we have e dot dd dt prime. Prime is a variable, and t is a fixed parameter, okay? Plus h dot dB dt prime. So we exchange that. It's going to be integral, volume integral of time integral dt prime e dot dd dt prime plus h dot dB dt prime, right? We have that. So this is a density, energy density, electromagnetic energy density. These we call the lowercase electromagnetic energy density. Sorry about that. So that's simply equals to the time integral plus h dot dB dt prime, right? Now we can change, we can make a change of variables. We can make a change of variables. Instead of integrating in t, we integrate in the space state, or space of states. Okay? So, for a time dt prime, we have that dt prime delta d delta t prime equals to a delta d. So instead of integrating t prime, we are going to integrate in space state, in which the integration variable is d. Same thing for the b, right? dt prime db dt prime equals to delta b. So the energy density can be written equals to the integrals on space of states. Plus integral from 0 to b final. The final value of b is the actual value of b at that time, instant of time. H delta b. So that's what it is. And here we can also separate the quantities into two quantities, the electric energy density and the magnetic energy density. We're just showing that that vector, the Poynting vector, the S, when you make the volume integral of the divergence, that means the flux either outwards or inwards, we show that it has a relationship to two quantities that we have already defined before, right? So this is something that we defined before. The energy density, electrical energy density, is this type of integral in space states. And this is the magnetic energy density, right? So that's what we have. WE equals to the integral as we did before. There's nothing new here. So that's what we have. Sorry, BF, right? Of H delta B. That's how we calculate energy in a given state. given by the vectors df and bf. We integrate in space states, and we have that. So what does Poynting's theorem give? Gives, right? So it gives this relationship here. Let me see, is it somewhere here? That's the integral form of Poynting's theorem. The flux of S inwards a surface that bounds a volume V, surface sigma that bounds a volume V, equals to the power flux, power exchange between field and current density, and the rate of change, time rate of change of the electromagnetic energy enclosed in the volume. If this flux is positive, it means that this rate of change is positive and that the field is giving energy to the carriers, right, to move them. The differential form is just going back, to the original relationship. It's just going back, just change that through Gauss's theorem. We're going to have the divergence of S. Then we have volumes here, right? This is a volume integral, so we're going to have only the densities. The minus divergence of S equals to E dot J plus the time rate of change of the energy density. This is lowercase, okay? Lowercase letter. This is uppercase. So this is energy density, time rate of change of the energy density, plus E dot J equals to minus divergence of S. So this is called the differential form of Poynting's theorem. Okay? So both of them, right? Poynting's theorem, either in integral form or in differential form. Very well. And just concluding here, right? So these are the formulas. Energy density is the sum of the electric and magnetic. Electric is calculated in this fashion. Here I made a different notation, right? Just to avoid using the lowercase f. So we have a variable E and G, and variable H and B, and the final quantities are without the primed D and B. Also, just recall, this integral doesn't depend on the path if we have a conservative system. So it means that for a conservative system, always we have this circulation in space state of E delta D equals 0 and circulation of H delta B in space state equals 0, right? And this is the scheme, right? Any function, you have the integral of f against, this is wrong here, I'm sorry, this is not right. This is a wrong notation here. This is the integration variable. So this is the actual value of G, which is the integration variable, which is, for instance, G is either D or B. Here, this is G itself, right? This is G, sorry, G prime. This vector, this blue vector here is G, okay? We have some special cases. If we have if media media 1 and 2, this is wrong. Well, this 1 and 2 is I don't know what is this. What is this? If the media are linear, either isotropic or anisotropic, the relations that we obtain are those, those that we have already derived before. One half of d dot E and one half of b dot H, either isotropic or anisotropic, sorry. So if the media are like this, then we can show that the energy density is given by those relations, right? I have done that before for isotropic media. So in the general case, we can write D like this and B like this one. And when you replace, for instance, the energy density, WE equals to, let's say, integral from 0 to D of E dot delta D prime. So D prime equals to epsilon 0 E prime plus P prime, which is the variables, right? So delta D prime equals to epsilon 0 E prime. Sorry about that. Epsilon 0 delta E prime plus delta P prime. If we put that in there, we're going to have W, the energy density, equals to epsilon 0, integral change now from 0 to E of E prime delta E prime plus integral from 0 to P of E dot delta E prime dot delta P prime, right? So that's what we have. So here the integral is going to be E squared over 2. So E, right? Final value. I'm going to write like this. E dot E, E squared, right? Over 2 plus this integral in space state, in which now you use P as the integration variable. So that's what we have. That's for the electric energy. Something similar is going to happen to the magnetic one. Plus then you have plus integral from 0 to M H d H prime dm prime. So that's what we have, right? That's what we have for the magnetic energy density. And then the electromagnetic energy density is going to have this formula here, right? 1/2 of EE epsilon 0 plus 1/2 mu 0 HH H dot H plus the integrals in space state of E delta P and H delta M, right? That's the general result for in general. Well, let's make an example. Let's try to calculate what would be the for a nonlinear medium that has an hysteresis loop. What is the typical energy loss in a cycle? You know, you have you can cycle. You can apply a voltage in a system that has a magnetic core that is made of a ferromagnetic material. Then you use these in transformers, right? So you can make something like this. Make transformers. You have a very simple one. A core made of magnetic material. Then you have a winding. Something like this. And have a number of turns in one side and have another one on the other side. Let's make it like this. So you can transform the voltage values using those structures, right? So you apply an AC current in the winding, then you have some result on the other side. But we have some energy loss due to the nonlinearity of this core. We can look at that, but looking into the hysteresis loop. something like this. The core has a hysteresis area like this one, in which H is the horizontal field, is the field, magnetic field, and M is the magnetization. Then in cycle, on a cycle, you can start here in the initial value, let's say, or you can start here and magnetize, then you start entering the loop. So you go from the initial state, you will reduce the field from H2 to H1. So you have, let's say that you go back through this curve here. When you go up, you go like this, right? Then you have a cycle. So the question is, what is the energy variation if I make a full cycle like this? Let's imagine that we have a fictitious agent that is changing the field, H field. You reduce the field, then you go back again until the initial value. It goes down to H1, it goes back again to H2. So I can make H1 equals to H2, and then you have a cycle like this. You saturate on one side and saturate on the other side. What's the energy change in a cycle? If this energy change is positive, it means that the agent is supplying energy to the magnetic material. That energy is supplied after every cycle, and eventually you cannot keep increasing this energy stored in the system, right? The dipoles increase the stored energy, but they give some to the lattice, to the material in form of heat that doesn't come back. So in steady state, the rate of change of power given by the fictitious agent is going to be balanced by the power dissipated, power loss in the magnetic material. Let's calculate that using this basic formula I just show you. This is the case of a magnetic material, so we are not going to consider these terms here. So the energy change is going to be only the magnetic contribution. You don't have this, then you don't have that. So we're going to look at these two terms here, right? So let's look at the magnetic energy density. That's going to give you some information on the volume. So you're going to have this type of expression, right? We can, that's the energy at a given final state F. Let's drop that subscript so we don't make we don't mix definitions here. Okay, so that's the actual value of field is H, the final value. The integral is, this is a variable, H prime, dm prime. Okay, we don't have any vector here also, because I mean we have a system. Let's say that the system is isotropic. You just apply the field in one direction, m is in the same direction. So in a closed loop, in other words, when I go from initial state to the final state and to the initial state again, I have a closed loop. So the field at the initial state equals to the field at final state. That's shown here in this picture, right? Initial state H equals H2, final state H equals to H2. So the integral, let's go back again, right? In a loop, the integral of H, delta H, in a closed loop is going to be 0, right? It's not only non-zero when you go from a different state between H1 and H2. If we go from H1 to H2 of H, delta H, this is going to give us 1/2 of H2, let's call it the value H2 dot H2 minus H1 dot H1. But if it's a closed path, it's going to be 0. So the first term, so you know, the energy change in which hi equals to hf is going to be mu 0 integral, a closed integral of h delta m. I'm going to drop the vectors, right, because the fields are collinear. So it's going to be h dm. So what is this? Let's look at the loop here. So let's make the closed integral. We're going to go from h2 to h1 through the upper loop, upper curve we called mu of h, is that function here. So we're going to have a first integral, which is the integral from h2 or between, let's change the variable here first, right? Let's change the variable. Let's change, because I'm changing h, I'm not changing m. So let's express this in terms of h. So you see that d for h times m equals to h dm plus m dh, right? So the integral of dhm, initial state to intermediate state going back, well, this is going to be the values of hm at the endpoints, right? So this is going to be 0, right? Because h at the endpoints is going to be the same. Let's look at the hysteresis. At this point here, h is h2, and m is this value here. This value here, right? Doesn't matter. I mean, the product m times h is the same in the initial state, in the final state. So this variation is 0. So it means that integral of h dm equals to minus integral of m dh. So what we have, the energy, this is minus mu 0 closed integral of m dh. That's what we want to calculate. Okay? So the energy, in fact, is not Wm, it's delta Wm. The energy density change in the whole cycle is going to be given by that, by this here. So let's continue here, sorry. So the energy change, the density and energy density change equals to minus mu 0 closed integral of m dh. So let's look at our hysteresis loop. So this is m, this is h. So we're going to, from h2, we're going through the upper curve, which is this one. Then we close like this, right? So this one we call the function m upper. U for upper is a function of h. This one we call the lower curve, m lower of h. So the one integral is like this. I start at initial state, I go through m upper through this curve, to this intermediate point P, let's say. Then we go integrate now from this value of h, which is h1, right? From h2 to h1 through mu, then from h1 to h2 through ml. So delta m is going to be delta Wm equals to minus mu 0 times integral from h2 to h1 of m upper of h dh plus integral of, I'm sorry, from h2, right? From h2, oh, that's correct, h2, lower limit is h2, upper limit h1. The other ones from h1 to h2, of m lower of h dh. So what is this? This is equals to minus mu 0. Well, h1 is smaller than h2. So let's change the limits here. It's going to give minus integral from h1 to h2 m upper of h dh plus same integral h1 to same limits h1 to h2 m lower of h dh. And then what is this? This equals to, I'm going to put the minus in evidence here, minus mu 0. Then you have mu minus ml from h1 to h2 m upper of h minus m lower of h dh. So let's identify what is m upper minus m lower is this distance here. So we are integrating, you know, this is very small, right? So this is the h. So this m upper minus m lower, right? That's this dashed rectangle here. So this integral is nothing less than the area of the hysteresis loop, right? Like here. So that's the integral we are making. M upper minus m lower, integration from h1 to h2. That's going to be this area, this origin area here. So it means that the total energy change is proportional, right? Have to do the calculation. That's what I just demonstrated to you. This is the area enclosed by the hysteresis loop. So if this energy density change is positive, the energy is supplied by the external source or the fictitious agent to the set of magnetic dipoles in the material, and you know that eventually steady state is obtained after several cycles. Energy supplied at a rate that balances the power dissipated in the material. So that's what's called the magnetic losses in the material due to hysteresis loss. Magnetic hysteresis loss is this, right? The fact that you have to follow different paths in a cycle, then you have that result. Okay, so that's one application of this electromagnetic energy formulation that we just developed. And then we are ready to start applying Maxwell's equations for time-varying fields. That's what we're going to do in the next upcoming lectures until the end of the course. So we conclude this specific lecture at this point. This was a little shorter than usual, but you know that this is balanced by the longer classes that we always practice also. So it's okay. In the average, you have the standard, duration. So I hope to see you next time. Until then, bye-bye.